Hello everyone, how's it going? My name is Dan the Tutor, on a mission to become the world's greatest tutor. In today's video, we've got a short one. I'm going to be talking about the dot product. Dot product shows up commonly in physics and calculus, specifically calculus 3. And there's a few definitions I could give for the dot product, so let me just introduce it the way that you'll most commonly see it in class. So first of all, the notation for dot product is A dot B. Looks like a multiplication symbol. It kind of is a multiplication symbol. Sometimes you'll see them draw it really thick to emphasize it's the dot product. But at the end of the day, it looks the same as a multiplication symbol. Sometimes you'll see little vector arrows above A and B, or whatever the variables are. This is because we do dot products with vectors as opposed to scalars. Now what's interesting is when you do a dot product, again, both of these examples are vectors, but when you do the dot product, the result is always going to be a scalar. And the reason why that's important is because what makes something a vector? That's right, it has both magnitude and direction, while a scalar is only going to have magnitude, no direction. And what this would look like if I had a picture, let's say I have vector A pointing straight to the right or the positive x direction, and vector B, let's say, points that way. And again, they're vectors, so technically they're supposed to have little arrows above them, technically. The dot product basically says, instead of the black arrow for B, let's say I have this blue one that is projected down here exactly onto the direction of A. Now this is my new B vector, which maybe I'll just call bx because it's in the x direction. And so basically what this means in the math is that A dot product with B, and again, I'll put the vectors here, but in the future I'm going to be lazy and I'm not going to draw them, but it means the same thing. A dot B is equal to AB cosine theta, where theta is the angle between these two vectors. So this is one definition for the dot product. Two vectors dotted together is A times B times the cosine of the angle between them. Which also means sometimes they give you the wrong angle. Let me explain. Let's say this is vector A, this is vector B, and instead of giving you this angle theta, which would make sense, sometimes they'll give you this angle theta and you need to find this angle here, usually by doing 90 degrees minus theta, because they're complementary angles. They add up to 90 degrees. But once you get that angle, 90 minus theta, then you can do AB cosine theta again. And one more very important thing that I left out. When I have A times B here, it is the magnitude of A times the magnitude of B. And I'll add that back in the formula right here, because that's very important. And that matters because there's two ways they can represent that. For instance, I could say A equals 6, and that points straight to the right, while B equals 5 at an angle of, let's say, 30 degrees. The magnitude of A is 6. The magnitude of B is 5, because I'm ignoring the angle. That's one representation they can do. Another representation they can do is, instead of giving an angle, they can say, for instance, 6i hat or x hat, depending on who your professor is. They both mean the same thing. It's 6 in the positive x direction. And then 5, maybe let's say it's 5i hat plus 3j hat or something, where I represents the positive x direction, j hat represents the positive y direction. And so then if you want magnitude here, you have to do Pythagorean theorem. And let me show you why. If I look at vector B specifically, it is a right triangle like this. 5i hat plus 3j hat means 5 is in the x direction, 3 is in the y direction. If I want the hypotenuse, square root of a squared plus b squared. I'm doing a lot of that in my head, so hopefully that makes sense. And that's going to be the square root of 34, which unfortunately cannot be reduced. But that's what the magnitude of B would be equal to, square root of 34. Magnitude of A is very simple, since it's only in the x direction. I don't even need Pythagorean theorem. Magnitude of A is going to be just 6. And then when I want to plug in this formula, a, b cosine theta, a is 6, b is root 34, and cosine of this angle. If you want that angle, I would recommend doing inverse tangent of the opposite leg 3 over the adjacent leg 5. This is from geometry. If it doesn't make sense, review arctangent, arcsine, arccosine. But you plug inverse tangent of 3/5 in a calculator, you'll get about 31 degrees, which will go right here. And then you can plug 6 root 34 cosine 31 in a calculator, and you'll get that that's about 30 for the dot product. Now, specifically when we have these I hat and j hat notations, like this example again, the best way to do it is usually not with a dot b equals ab cosine theta. This is usually the worst way to do it if you have I hat and j hat or x hat and y hat notation. What should you do instead? I'll show you. If I have a dot b, and both a and b are vectors, where this is 6 I hat dotted with 5 I hat plus 3 j hat, then the way you do this, it's a special kind of foiling. You basically just multiply the I hats together. So 6 times 5, which is going to be 30, plus the j hats. Technically this is 0 j hat, it's a weird example. 0 times 3, which is just 0. So the answer is just going to be 30, which is the same answer we had earlier. I'll scroll up. We said this was 30 right here, doing the AB cosine theta method. But this method, where I just combine the i's and the j's independently and then adding them together, I can do this a lot faster for I hat and j hat notation. Now let me guess, that's a little confusing, right? So let's just do a few more examples of that, and I think you'll get it. Let's say I have vector c, which is 2 I hat minus 5 j hat, and then vector d is equal to negative 3 I hat minus 2 j hat. How do we do the dot product of c dot d? I'll tell you. First, I'll set up this little expression that looks like I'm foiling, because I technically am foiling, but doesn't look like it. And then you just only combine the i's, so for instance 2 times negative 3, and then plus the j's, in this case negative 5 times negative 2, giving me negative 6 plus positive 10, because they're both negative. Negative 6 plus 10 is positive 4, and that's the answer for c dot d. And so basically 2 questions you should have from this is, number 1, what happened to the I hats and the j hats when I moved from this step to this step? And number 2, why didn't I do the OI in the FOIL? In other words, why didn't I do 2i times negative 2j, and why didn't I do negative 5j times negative 3i? The short answer is you never do those two, but the reason why, and also the reason why the I hats and the j hats are gone, is because of this. Technically what you're doing when you have 2 I hat times negative 3 I hat, and you're multiplying these, it will be negative 6 I hat squared, just the I hat squared. And famously, I hat squared is just 1. I don't have a proof for that other than this is just something we know. Same thing with j hat squared, that's also 1. But then when I have something like 2 I hat times negative 2 j hat, you'll get negative 4 I hat j hat. I hat j hat is famously 0 because they're perpendicular to each other. Same thing with j hat I hat, that's also 0. Or any combination of the k hat, which is for the z dimension in 3-dimensional physics or calculus, that's also going to be 0. So then one more example. Let's see if you can do this one without me. Let's say vector e is equal to 13 I hat minus j hat plus 6 k hat. In other words, it is 3 dimensions because k hat is the 3rd dimension. And then f hat, let's say that's 2 I hat plus 4 k hat. You'll notice the j hat is missing. I want you to think about what we do there. So go ahead, find vector e dot product with vector f, pause the video, and when you're ready to see the solution, unpause. Okay, so here's what we do. First of all, I'm combining the 13 times 2 for the I hats. That's going to be 26. Remember, there's no I hat here because that's technically I hat squared. I hat squared's 1, so don't write anything. For the j hats, this is a -1, don't forget that. So it's plus -1 times 0, because f doesn't have a j hat. I guess you could write 0 j hat if you want to, but it's going to be 0 for the j portion. And then plus, for the k's, 6 times 4. And then I basically just simplify and add these together. 26 plus 0 plus 24. We're going to get 50, and that's our final answer. Hopefully you got that. If not, just try it again, and hopefully it makes sense the second time. Finally, two last things I want to say. How this applies to, for instance, physics. The most famous example of the dot product is work, because work is famously force dot product with the displacement vector. Both of these are technically vectors, but a lot of times we're lazy and we don't put the vector above them. And the reason why this is so important is because the equation you see in most textbooks is FD cosine theta. Because remember what we said earlier at the very beginning. Another way you say A dot B is magnitude of A, magnitude of B, cosine theta. And technically, yes, it is magnitude of both F and D, force and displacement. That's how it applies to physics. And then with calculus, specifically Calc 3, multivariable calculus, you'll usually see something like this. 3, 1 with the angled brackets, dot product with 2, 8 or something. And what this is basically saying is this first vector is 3i hat plus 1j hat, dot product with 2i hat plus 8j hat. And I don't know why we write it with these angled brackets, but this is the notation we commonly see in Calc 3. And again, this is for a two-dimensional problem. If it were a three-dimensional problem, it would be like 3, 1, 0, angle brackets, dot product with 1, 9, -5 or something. And again, very quickly, it's 3 times 1 plus 1 times 9 plus 0 times -5, giving me a final answer of 3 plus 9, 12. And if you know what you're doing, you can do these problems very quickly. And if you don't know what you're doing, then rewatch the video and hopefully, again, it makes sense the second time. So that's all the problems I have for today on dot product. In the next video, I will be talking about the cross product, which is the much harder version of the dot product. So stay tuned for that. Have a great rest of your day, and I'll see you in the next video. Take care, and bye-bye.